welcome all of you to the video lecture series on computational fluid dynamics, development, application and analysis. The title of this lecture is Computational Fluid Dynamics on a Staggered Grid. The details of this lecture can be found in the chapter 9 of the companion book, chapter 9 on CFD on a staggered grid of the book Introduction to Computational Fluid Dynamics, Development, Application Analysis. For the present video lecture series on first course in Computational Fluid Dynamics Development Application Analysis that is presented in the YouTube channel CFD Made Easy, we are towards the end of the lecture series. Present lecture is on the last topic, topic 6 on computational fluid dynamics on a staggered grid. I had started this lecture series with topics in 3 different parts. The part 1 on introduction and essentials, which consists of 2 topics. Topic 1 on introduction to CFD development application analysis, part 2 on topic 2 on essentials of CFD. So this is the part 1 of this lecture. And in the part 2, I had gone from introduction essentials to computational heat transfer, where topic 3 was on computational heat conduction and topic 4 was on computational heat convection. The last part of this lecture series is on computational fluid dynamics and heat transfer. The previous lecture was on topic 5 on physical law and discrete math based finite volume method for CFD. The present lecture is on CFD on a staggered grid. The present topic on CFD on a staggered grid will consist of 2 different parts, where in the part 1, here I'll present the 3 different subtopics. I'll start with the challenges in the CFD development. Then I'll move on to a staggered grid, which was proposed as one of the first remedy to resolve one of the challenge in CFD, that is called as pressure velocity decoupling. Although the previous topic presents the physical law and discrete math based finite volume method, but when we consider a staggered grid, this algebraic formulation gets modified. So for a staggered grid, here I'll present the physical law and discrete math based finite volume method. So this corresponds to the part 1, where I'll present this 3 subsections in this lecture, and in the part 2, the flux based solution methodology as well as the initial and boundary condition will be present. If you look into the history of development of computational fluid dynamics, you'll find that there have been many challenges, especially in the beginning of the CFD development, which is around 50 years ago. So I'll start with the discussion on the challenges for the CFD development. We are moving from computational heat transfer to computational fluid dynamics. Note that the present part on computational heat transfer, where we have considered computational heat convection, we have avoided considering the flow. So we have considered computational heat convection with a prescribed flow. So in the computational heat transfer that was presented in the previous topic, the flow field was prescribed. So the only conservation law that we discussed was the energy conservation law. Now when we are moving from computational heat transfer to computational fluid dynamics, note that there are 2 additional laws which now will appear for this topic. Those 2 additional laws corresponds to the mass conservation law and the momentum conservation law. Now, if you compare the energy conservation law with the momentum conservation law, you should note that energy conservation law is a scalar law and momentum conservation law is a vector law. And I had presented in my previous topic that when you compare a scalar law with a vector law, the flux term in a scalar is a vector, whereas the flux term in a vector law is a second order tensor. However, any vector law we apply component by component. So we will apply the momentum conservation as x momentum conservation, where we'll take the x component of the second order tensor as the flux term, where finally it will get converted into a vector. This I presented in detail in my previous topics. So another point to note is when you consider the momentum equation, there is a non-linearity which appears in the advection term. So one of the challenge in CFD development has been in the nonlinearity, which corresponds to the advection term. And then when you move from computational heat transfer to computational fluid dynamics, the additional conservation law that you encounter is the mass conservation law. Now, this mass conservation law, this lecture series is presented for an incompressible flow. Now, in this mass conservation law, basically, I'll present that one of the challenges to convert this mass conservation law as a log, or we have to derive the algebraic formulation for pressure from this mass conservation law. That is another challenge in the development of CFD. And the last challenge in the CFD development is an issue which is called as pressure velocity decoupling. So all these three challenges that people encounter during the initial days of CFD development will be presented in this lecture series. This lecture series corresponds to the first course in computational fluid dynamics. So these are some initial challenges that people encounter in the beginning of the CFD development. So let us get started. The first challenge that I would like to highlight is the advection term in the momentum equation, which introduces nonlinearity. The second challenge is that there is no explicit physical law and the resulting algebraic equation for pressure. And I will introduce that when people started converting in the early days of CFD development, people encountered issue which is called as pressure velocity decoupling. So these are the three challenges which were encountered in the initial days of CFD development. So let us get started with the first challenge, nonlinearity, which you encounter in the advection term in the momentum equation. The advection term basically consists of the momentum flow rate, which is the product of mass flow rate and the velocity. So if you consider the x momentum conservation, you find that in the x momentum flow rate consists of the product of x momentum flux and the surface area, and the x momentum flux is given by m vector u vector, which is a second order tensor. But this is a momentum flux, but when you apply it for x momentum, you have to take a dot product with I, and this becomes x momentum flux. So this x momentum flux is shown here. Now, when you see the x momentum flux, it's a product of mass flux and the u velocity. Now the mass flux also consists of a normal velocity. So it consists of the product of u square, velocity square, and so that's why it becomes a non-linear quantity, because velocity is an unknown quantity, and so the advection terms is a non-linear. It consists of a quadratic variable in terms of the unknown variable. So this introduces a non-linearity where depending on the explicit, implicit, or Crank-Nicolson you are using, this u velocity is taken for, if you are using implicit method, it could be an implicit. But note that to avoid the non-linearity, the technique that is used is this mass fluxes are always taken explicit in the advection term. Okay, so this is corresponding to the x momentum flux. When you move to y momentum conservation, you encountered y momentum flux, and in the y momentum flux again you have a product of mass flux. Now in x momentum you have a product of mass flux with u velocity. For y momentum flux you have a mass flux with the product of v velocity. And here again you should note that the advector variable, which is u for x momentum and v for y momentum, can be implicit, but to avoid the non-linearity, we always take this mass flux from the previous picture or from the previous time step velocity distribution. Okay, because if you try to make it implicit, you will find that it will become quadratic, and then you will have to you will not be able to do an algebraic formulation, and it consists of a non-linear term. So one of the technique to avoid the non-linearity is to consider the mass flux as explicit. This is corresponding to energy equation. Energy equation, you have a product of mass flux with the temperature, which gives you an enthalpy flux. So here again, the mass flux, you can note that this is corresponding to the previous time level. So by taking the mass flux as explicit, we are avoiding the nonlinearity. This is the final discretized algebraic formulation that I presented in my previous topic, where you can note that the nonlinear term, which is corresponding to advection, because you have a product of mass flux with this phi as u velocity for x momentum, v velocity for y momentum, and temperature for energy equation. We are always taking mass flux as explicit, whereas this phi can be has a power of n. For explicit, for implicit it will be n plus 1, and for Klein-Nicholson it is n plus half. So we avoid the nonlinearity by considering the mass flux as explicit for momentum conservation as well as for energy conservation. The second challenge, which was in the early days of CFD development, is that you do not have an explicit physical law and the resulting algebraic equation for pressure. You have laws which says rate of change of x momentum, rate of change of y momentum. You have law which says rate of change of enthalpy. So when you have law which talks about rate of change of x momentum is basically product of mass and u velocity. So you get an idea that from the rate of change of x momentum, you can create a movie for u velocity. From the rate of change of y momentum, you can create a movie for v velocity. From the rate of change of enthalpy, you can create a movie for temperature. So you have the momentum conservation as the law. It's a vector law. So the movie that you create, this momentum conservation law is like a mother, and the child is also a vector, which is a velocity. So velocity is the output, is the so this momentum conservation law gives an idea that this is the law for the and from which this is the algebraic formulation that I had presented in detail in the previous lecture, and I'm showing hereby showing you the final algebraic equation. So you can see that for velocity we have an explicit law, momentum conservation law. We have an explicit algebraic equation as shown here for velocity. For energy for the temperature, we have an explicit law, that is energy conservation law, and we have an explicit algebraic equation that is presented here for temperature. But we do not have any law which talks about rate of change of pressure. And since we don't have any law which talks about rate of change of pressure, we are not able to algebraically formulate the algebraic equation for pressure. So this is one of the biggest challenge in the development of the early days of CFD. So we are left with a third law, which we have to use it for pressure. So the mass conservation law, although if you look into the mass conservation law for an incompressible flows, and the present video lecture series is on CFD for incompressible flow, you find that there is no unsteady term, because in incompressible flow, when you consider rate of change, there are two rate of change. Rate of change of mass stored inside the control volume, where you have rate of change of density, which is equal to 0. So so if you consider mass conservation law based algebraic equation for incompressible flow, there is no unsteady term for incompressible flow, and moreover the remaining term, the net mass flow rate living across the surface of the control volume, if you consider, and this is the algebraic formulation corresponding to that. This I presented in detail in my previous video lecture. So you see that you want to use this algebraic formulation for pressure, but the algebraic formulation that you have obtained consists of the normal velocity normal to the surfaces, u velocities and v velocity. It does not consist of any pressure. So note that for pressure we do not have an explicit conservation law, and we do not have an explicit algebraic equation. Whatever algebraic equation we have, whatever law we are left with mass conservation law, and that mass conservation law lead us to this algebraic equation, which does not have pressure as a term in this equation. So one of the biggest challenge in the early days of CFD is how to convert the steady form of the mass conservation law based algebraic equation as an algebraic equation for pressure. However, if you consider a compressible flow, in compressible flow, the first rate of change, you have a rate of change of density. So from that, if you do an algebraic formulation, for compressible flow, the mass conservation law based, you can do an explicit algebraic formulation where this is for density. So for density, density is not a, it does not vary for incompressible flow in space and time, but for compressible flow, it varies in space and time. So the mass conservation law, it turns out that for compressible flow, it is a explicit law for density. So for a mass, for compressible flow, you can get the velocity from momentum conservation, temperature for energy, and you can get the density distributions from the mass conservation law. So mass conservation law is an explicit law for density. And it leads into an explicit algebraic equation as shown here for density. Whereas for compressible flow, this unstudied term is zero, and you do not have an explicit conservation law as well as an explicit algebraic equation for pressure. So compressible flow mass conservation is used to get density variation, and an additional equation is used to recover the pressure from the density field. So you can use mass conservation law to create a movie for density, and from once you know the density and temperature, there is an expression which is called as pressure is recovered from pressure density relationship, such as if you use an ideal gas law, you have P is equals to rho RT. So you can obtain the movie for density from this equation and temperature from energy equation. And once you know rho and T, you can use the pressure density relationship. If you are using such as ideal gas law, P is equals to rho RT, you can create a movie for pressure distribution. So there is an additional constitutive relationship, pressure density relationship, which is used along with the conservation law for CFD for a compressible. So this lecture series is focused on CFD for incompressible flow, not on CFD for compressible flow. However, you can see that the challenge probably is much more for CFD in incompressible flow as compared to compressible flow, due to the fact that for compressible flow, the mass conservation law is an explicit law and leads us to an explicit algebraic equation for density, and the pressure is recovered from pressure density relationship. So for CFD for compressible flow, the procedure seems straightforward. However, for CFD for incompressible flow, you end up with this situation where the challenge is for an incompressible flow CFD, the challenge is to convert steady state mass conservation law based formulation as an algebraic equation for the unsteady pressure field. So your challenge is to develop steady state mass conservation law based algebraic formulation for the unsteady pressure field. This will be presented in detail in the part 2 of this lecture. So after starting with the challenge on non-linearity and no explicit physical law and resulting algebraic equation for pressure, I'll present the last challenge in the early days of CFD, that is called as pressure velocity decoupling. In the previous lecture on finite physical law and discrete math based finite volume method for computational fluid dynamics and heat transfer, I have presented that when you move from computational heat transfer to computational fluid dynamics, you encounter two additional laws. One is mass conservation and second is the momentum conservation. And I have presented that there are certain ideas from computational heat transfer that you can directly extend to momentum transport, because the energy transport and momentum transport, basically they corresponds to a transport process where when you look into a transport process, there is a driver and there is a passenger. And I had mentioned that the transport mechanism, which gives you an idea about the driver to the transport process, there are two types of transport mechanisms or driver to this transport process. One which is called as random motion of molecule-based diffusion. And the second is the bulk motion, which basically leads to the onset of flow or the mass flow rate. So the random motion leads to conduction, and so whatever approximation that we have used for calculating the conduction fluxes, and so we extend in the previous topic I had mentioned that the idea of molecular transport mechanism based conduction can be easily extended to calculate the viscous forces for the momentum conservation, and the mass flow rate based advection transport, which corresponds to enthalpy flow rate in energy transport can be extended to momentum conservation for momentum flow rate. And I had mentioned that the advection scheme that was presented in computational previous topic on computational heat convection can be directly extended. So these are the things which you can extend the diffusion and the advection. But other than this, there are some additional things which you encounter when you move from computational heat transfer to computational fluid dynamics as well as heat transfer. Is the mass conservation law, you have to use certain approximations which are new to this topic. And second, when you compare the energy equation and the momentum equation, you encounter pressure only in the momentum conservation, not in the energy conservation. So the pressure comes as an additional variable when you move from computational heat transfer to computational fluid dynamics and heat transfer. So in the previous topic, I had mentioned that for the mass conservation, we have used a second approximation, and I have also mentioned that for pressure also, we have used certain second approximation. Now, in the next couple of slides, I will show you that this second approximation for the mass flux and the pressure leads us to a numerical problem, because people, when they use those approximations, they found some unrealistic numerical solution. So that is called as pressure velocity. So with this background, let us consider the finite volume method that I had presented for mass conservation in the previous video lecture on physical law and discrete math based finite volume method for CFD. So when you apply the finite volume method for mass conservation, I have presented that you use linear interpolation as the second approximation for the normal velocities at the phase center. In the previous lecture video, I had presented that if you consider elemental control volume of width delta x and delta y, and this straight M is called as mass flow rate, and this is given as in terms of the mass flux and the surface area. This mass flux mx is equals to rho into u, and the my, the mass flux in the y direction, is equal to rho into v. So for the incompressible flow, when you talk of rate of change for mass conservation, there are two rate of change. First rate of change is rate of change of mass stored inside the control volume, which is 0 for incompressible flow. The second rate of change is net mass flow rate leaving across the surface of the control volume. So if you want to calculate net mass flow rate leaving across the surface of the control volume, then you have to take the mass flow rates from the positive surface and then subtract from the negative surface. So you'll get this rho ue delta y minus this and this minus this, which is shown here. So the net mass source, which is the net mass flow rate leaving across the surface of the control volume, should be equal to 0. And when you convert the mass flux as a product of density and normal velocity, you get finally this expressions. So note that by using the first approximation, you have converted the mass flux acting on a surface by its value at the centroid of the surface, which is represented here, the centroids as east, west, north, south, as shown here. Now, the second approximation is to calculate the value of the velocities, the normal velocities which you encounter in the mass fluxes. So if you want to calculate UE for a uniform grid, which is shown here, where you can see that the control volume, neighboring control volume size are same. So calculate UE, if you draw a horizontal line, you find that this point E is exactly in between capital E, and so these circles are like grid points or pixel for U and V velocities. So if you want to, and you want to calculate at this center where you do not have any grid point. So to calculate UE, if you draw a horizontal line, you encounter this capital E and capital P are equidistant from E. So one of the simplest approximation that you use a linear interpolation. This UE is equals to U capital E plus U capital P divided by 2. This UW is U capital P plus U capital W divided by 2. Here for the north and south, you need V velocities. So calculate V velocities. V at small n is equals to V capital N plus V capital P divided by 2. And similarly for the subsurface. So if you do for a uniform grid, if you do a linear interpolation, what you find is this is for UE, this is for UW, this is VN, and this is VS. So in this, if you see this UP, there is a negative sign in between, so it cancels down, and VP cancels down from the second term. And then finally, you end up with a velocity with an equation from mass conservation, algebraic equation from mass conservation equation, which consists of U capital E and U capital W, U capital N and Vs. So you, so when you applied the mass conservation law based, when you come up with an algebraic formulation, which is presented here, you have applied the mass conservation law to a grid point or a pixel P. But note that the equation that you have obtained consists of the velocities, U velocities of capital E and capital W. It does not consist of the velocity of the same grid point. And so if you note that this W and P are adjacent grid point, P and E are adjacent grid point. If you see E and W, they are alternate grid points, because in between W and E there is a grid point P. So you end up with an algebraic formulation with velocities. For mass flux, it is a normal velocity at alternate grid points. Okay, so you get UE and UW. There is no UP. Here you have VN and VS. You don't have VP. So, and you end up with an algebraic equation for the normal velocities in mass conservation law-based algebraic formulation, which consists of velocities at alternate grid points. Other than mass conservation, you, as compared to computational heat transfer, for this topic, you encounter pressure term. Now, similarly in pressure, if you want to calculate net pressure force in the positive x direction, you take the control volume and draw the arrows for pressure acting on the vertical surface, because there only the pressure acts on the horizontal direction, and pressure is always normal and compressive in nature. So this is the pressure force acting on the west surface, this is the pressure force acting on the east surface. Now, here again for a uniform grid, so the net pressure force is given by PW minus PE into delta Y. Now, to calculate PE, you do not have any grid point, so you have to use some approximation similar to what we have used in the previous slide. If you use a linear interpolation, this PW is equals to PP plus P capital W divided by 2. This P is P capital E plus P capital P divided by 2. So here again, the PP cancels down from this, and you end up with a algebraic formulation for pressure term, which again you can see now the net pressure force which is driving the velocity, the pressure gradient for in the x direction and y direction. The algebraic formulation is presented here for x momentum conservation. This is presented for y momentum conservation. Here again you see that it is consisting of pressure of W and E. W and E are alternate grid points, because there is another grid point which is P in between. Okay, so here you end up with an algebraic formulation with pressure at alternate grid points. Now, when you have pressure at alternate grid points, so you can see that this is the algebraic formulation for pressure at alternate grid points, which is used in X momentum conservation. So in the previous lecture, I presented in detail that this is the algebraic formulation finally obtained from X momentum conservation. This is the algebraic formulation finally obtained from Y momentum conservation. Now, ultimately, this pressure is used to obtain a movie or a data or velocity field for U velocity. So you end up with, if you use a linear interpolation as the second approximation to calculate the pressure at phase centers in terms of neighboring cell center, you end up with a situation where from momentum conservation, the velocity which you are obtaining is at a grid point P. But the velocities to obtain this velocity is the pressure that you are using are at alternate grid points. So there is some numerical issues which I'll present in detail later, which lead to certain unphysical solutions. So to give a reason to this unphysical solution, they came up that this second approximation is causing the problem, and because when you have pressure and normal velocities at alternate grid points, it so turned out that the data that you obtained after solving this algebraic equation indeed obeys this equation, but it is unphysical in nature, because so they came up with a reason saying that to calculate the velocity at a grid point P, since these velocities are not involving the pressures of the same grid point, that is P at this point P, there is a breakage in the communication between the pressure of the same grid point with the velocity of the same grid point. And this is the way they said that this is called, they called it as a pressure velocity decoupling. So the breakage in the communication between the velocities of the same grid point with the pressure of the same grid point, because you can see that UP equation does not involve pressure at point P, VP does not involve pressure at point P. So this is the reason they called it as a pressure velocity decoupling, because the velocity of the same grid point is not coupled with the pressure of the same grid point in this algebraic formulation. The decoupling results in an unphysical oscillatory solution that I'll present in the next slide, which is a superposition of the correct velocity field and the pressure field with a physically unrealistic oscillatory type of flow field. So as I mentioned, that if you use this algebraic equation, people have found that they get a solution which is of course obeying these equations, but which is a superposition of the correct velocity and pressure field, which is superimposed with a physically unrealistic oscillatory type of velocities and pressure. Okay, so you get an additional solution which is oscillatory in nature, which finally gets superimposed with the correct field, and you get an unphysical oscillatory solution. I'll present this in detail in the next slide. So let us consider an example of the checkerboard or the oscillatory velocity and pressure field inside a computational domain, and explain you that how this velocity and pressure distribution obey the mass, the algebraic formulation that we have obtained for the mass conservation and the pressure gradient. So let us suppose you have a velocity distribution like this. So if you are applying the algebraic equation that we have derived from mass conservation, now you can see that if you apply, this is a point P, there is, suppose this is a point E, this is W, this is N, this is S. So if you apply, let us suppose this number distribution is for the velocities. These are the, let us say, U velocities, this is a V velocity. So if you apply to a particular point, you can see that if you take the difference, is U capital E minus, if you, let us say this is the rho, this is the velocity, if you consider this velocity and the surface area is same on this two, and density is also same. So if you take the difference of the mass flow rate from the east surface and the west surface, and also from the north and the south, you will see that this additional oscillatory velocity field also obeys the algebraic formulation that you have derived from mass conservation. So along with the correct velocity field, this oscillatory velocity field also obeys the linear algebraic formulation for mass conservation that we have used, that we have obtained by using the linear interpolation as second approximation. Now, if you consider this number distribution as a pressure distribution, and if you are applying, let us say, X momentum equation at this point P, then also you can see that this oscillatory pressure field is basically giving a net zero pressure force in the X direction and net pressure force, zero pressure force in the Y direction. So this, if this number distribution, in previous case I had considered this number distribution for normal velocity. Now if you consider this number distribution as an example for pressure distribution also, where you can see that these numbers are alternately repeating. In the X direction you can see here it's 100, here again 100, here 100. This is 400, then alternate value is 400. Here you can see the alternate values are 1 in the vertical direction. It is 5 in the vertical direction. Here again it is 1. In this direction you have alternate 1. Here it is 5. Here it is 400. So you have a checkerboard or the oscillatory number distribution, and such type of number distribution, if they are there for the pressure and the normal velocities on the surface, it so turned out that this also obeys the the finite volume method based algebraic formulation for the mass conservation, and for the momentum conservation they leads to the net pressure force as 0, So along with the correct pressure distribution, you get an oscillatory this type of pressure distribution which is superimposed. Now, such type of checkerboard distribution over and above the correct velocity and pressure field. Note that here I have shown you the second part which gets superimposed with the correct. I am not showing you the correct velocity and pressure field. So this type of checkerboard distribution over and above the correct velocity and pressure field also obeys the linear approximation based formulation. We note that we have used linear approximation as the second approximation for mass fluxes in mass conservation, and we have also used this for the pressure term in the momentum conservation. This second approximation based formulation for mass conservation and momentum conservation, which we have used. So this checkerboard fields leads to a physically unrealistic oscillatory velocity and pressure field. So this is called as the pressure velocity decoupling because you end up with an equation for velocities at point P where the value of pressure at capital P is not involved, and it so turned out that the mass conservation equation consists of the normal velocities at alternate grid point, not the adjacent grid point, and for momentum conservation, pressure which are involved in the equation for the velocities, the pressure are at alternate grid point. So this velocities at alternate grid point, this pressures at alternate grid points leads to the pressure velocity decoupling because such type of this checkerboard type of velocity and pressure field, they do obey the mass conservation and momentum conservation. So they get superimposed toward the correct velocity and finally lead us to the physically unrealistic oscillatory velocity and pressure field. So one of the first remedy that was presented for this pressure velocity decoupling. So let us go to the next section where we'll introduce one of the first remedy to this pressure velocity decoupling, where we basically wanted to avoid algebraic formulation which involves the pressure of alternate grid points and the normal velocities of alternate grid point in the algebraic formulation. So one of the first remedy that was proposed if you look back to the history of development of CFD is called as staggered grid. So this topic is on CFD for a staggered grid. So in a staggered grid, the idea that was proposed is that let us not use same grid point or same pixel or same control volume for the mass conservation, momentum conservation, and energy conservation. Let us, so it is like, let us use differently located pixels for pressure, velocities, and temperature. So let us consider, so on staggered grid, it was proposed that if you consider this yellow circle not as a pixel or grid point for all the flow properties, velocities, and pressure and temperature, let us consider it, let us say if you consider it for pressure. So let's suppose if we call it as this is the pressure control volume. So from this control volume, or this yellow circle is the pixel for pressure, and this is the grid point corresponding to point P. In a staggered grid, it was suggested that let us stagger the control volume. Let us not use same pixel. Let us locate the grid point for v velocities on vertical phase centers. So when you consider this vertical phase center, so here let us suppose we have a pixel for u, and we have pixel on this vertical phase center also. So this green square is like a pixel, and then this grid control volume is like the control volume in which you will apply the X momentum conservation. And this is for Y momentum conservation, or the grid point for velocity was proposed in a staggered grid on horizontal phase center. So let's say this is red inverted triangle is a pixel for V velocity, and this red control volume is the control volume where we will apply the Y momentum conservation to derive the algebraic formulation for the V velocity. Okay, so this way in a staggered grid, the pixels or the grid point and the control volume and the associated control volume, because these pixels or grid points are at the centroid of the control volume, are staggered in space. The U control volume is staggered by delta x by 2 on a uniform grid, and the V control volume is also staggered by delta y by 2. So in this yellow control volume and this yellow pixels, yellow circle as the pixel or grid point for pressure, the way we have defined the pixels for u and v velocities, note that here I have a subscript p, but here this green square and red inverted triangle, this I had already shown you as pixels for qx, qy, hx, hy. Green square I had presented in my previous topic as the pixel for qx, and later on when we went to convection, I said that this is also pixel or grid point for hx. This red inverted triangle in conduction, it was for qx, and then when we went to convection, it is for hy. So qy and hy for as the pixel for this triangle as the pixel for qy and hy. This red triangle, green triangles for qx and hx. So in the previous topic, I had mentioned that while implementing in the code, we want to use a single running indices. So what I have said is that for the positive faces, the pixels which are located at the positive faces, the running indices will correspond to the grid point on which it is lying at the center, at the faces of as the positive faces. So these are the positive faces. So this will be UP, this will be VP, and because east and north faces are the positive faces, so the velocities which are presented on the positive faces, they have the same subscript. Now, if you consider you have another green square here. Now, this green square is a positive face of the west control volume. So here we will have UW, and if you consider another, because this is a horizontal surface, so here you will have another triangle. This is a positive surface of the south control volume. So this will become the VS. So I'll show you here. So this is UP, and as I said, this is VP because the pixels for the positive faces, they corresponds to the running indices. That is, wherever I have P, it is I comma J. So this is UI comma J, this is VI comma J. So they are on this. If you consider, so you have, because these green squares are located at vertical face centers. So you have UW here. If you have a green square here, this is the east face of the control volume, which is W. So here you will have UW. If this is VP, as I said, you have a triangle, red triangle here. This is a positive surface. This is a north surface of a control volume, which is denoted by S. So this will be VS. Okay, so we are basically extending the convention that I had presented for in the previous topic on computational heat transfer, where while representing Qx, Hx, Qy, Hy, we have used a convention. In the same convention, we are extending for U and V for this topic. So this is the control volume where you will apply the mass conservation, but this is also considered called as a scalar control volume. Along with the mass conservation, you apply this control volume for energy conservation also. So later on, I will show you that we do algebraic formulation for mass conservation and energy conservation using this control volume. Now, this second control volume, which is presented here, is the staggered control volume, which is like a green control volume, and the centroid is giving you the pixels or the grid point for u velocity. If this is UP, then actually this is basically this UP. You have this vertical line which is presented here, which is west face for U control volume, is basically here. So you have PP line here. If PP is here, UP is here. Then you have VP, which is in this corner. Okay, and if this is PP, then this grid point will be PE. If this is VP, this will be VS. This is PE. If this is PE, then the north surface, which is a positive surface, you will have a triangle here, and the subscript for that triangle will be VE, and another triangle will appear here, which will be VSE. So I am showing you a control volume along with all the pixels or grid point that are associated within that control volume. Okay, so you can see that the normal velocities for the P control volume, pressure control volume, they are lying on the phase centers. And on a U velocity control volume, which is applied for mass conservation, the pressure is lying on vertical phase center, and V velocity is lying at the corners. Now, if you consider for Y momentum, we use this red control volume and the pixels or the grid points as V. Note that we have used this pixel for Qx in the previous topic, QXHX, and we have used this for QYHY. This is VP, you have here PP, here PP. And if you have this is PP, this will be U capital E. So this corner will be U capital P. This will be U capital W. And here you will have P, because if this is P, this is P, this will be PN. This is on the north side. This is PN. If this is PN, you will have here UN. And this will be U and W. Because this is on the north surface, but on the west side. This is U and W. So here I am showing you that for a red control volume, which is used for Y momentum conservation, the pressure is lying on the horizontal phase center and U velocity is lying at the corners. So if you see the staggered control volume for pressure, U velocities and V velocities, this is the control volume where we apply the mass conservation, and it so turns out that to calculate for applying the mass conservation, when you want to calculate the mass flow rate, on the vertical surface you calculate the mass flow rate in the x direction, and so here the mass flux that is involved is mx. Now, mx involves u. So when you have to calculate mxe, the velocity small ue, which is the east surface of this control volume, the pixel or the grid point for the U velocity is already defined. Okay, so you do not need second approximation for the mass fluxes while applying the mass conservation law. Because in the pressure control volume where you are applying where you want to calculate the mass flow rate, what you are finding is that at the centroid of the surfaces, you have already defined the pixels for the normal velocities. So there is no need for the second approximation to calculate the mass fluxes. When you use the U control volume to apply the X momentum conservation, you want to calculate the net pressure force acting in the positive X direction. Now to calculate the net pressure force, basically you take pressure on the vertical surface. Now here again you can see that the pixels for the pressure is already defined at the vertical surfaces. So here again note that to calculate net pressure force in the X direction, here when you calculate P small w, P small e, P small w is equal to this P capital P, this P small e is equal to P capital E. So when you calculate net pressure force, note that the second approximation for pressure is not needed. So, and similarly in Y momentum equation, when you want to calculate net pressure force in the positive Y direction, basically you take pressure on the horizontal surface, and at the centroid of the horizontal surface, you already have pixels or grid point for pressure. So with this staggering, what you have already done is you have staggered the pixels for P, U, V in such a way that while applying the momentum conservation and the mass conservation and the momentum, X momentum conservation and Y momentum conservation, the grid points are located in such a way that you don't need second approximation for mass conservation and the second approximation for pressure in the momentum equations. So this way, when you use a staggered grid, the second approximation, note that we have second approximation for the various fluxes. In the previous topic, I had mentioned this second approximation as an advection scheme for advection fluxes, as a central difference scheme for a diffusion fluxes. Now, when we are coming to this topic, we are encountering two new fluxes. One is mass flux and the second is pressure. This additional new fluxes, if you use linear interpolation, I had mentioned in the previous slide that it leads to the problem of pressure velocity decoupling. So note that by staggering the grid, you are the second approximation in the mass conservation equation and momentum conservation laws based finite volume method is completely avoided. So when you use a finite volume method, which is from mass conservation and momentum conservation, the second approximation is completely avoided. Note that this is avoided for mass flux and pressure, not for the diffusion flux and advection flux. Okay, because this second approximation were leading to the problem of pressure velocity coupling. So this is a staggered control volume. This corresponds to the figure 9.3 of the companion textbook. And this is the control volume in which we apply the mass conservation law as well as the energy conservation law. This is called as a scalar control volume. So this yellow circle is not only the pixels for pressure, it is also considered as a pixel for temperature. This is a control volume where we apply the X momentum conservation. And this is the control volume for Y momentum conservation. Note that the width of the control volume, the way we have, note that we use one running indices not only for the U, V, and P, but we also use one running indices for the geometrical parameters. I have mentioned that the geometrical parameter for a uniform grid is in a uniform Cartesian grid, you only have a delta X and delta Y. But when you consider a non-uniform Cartesian grid, then the width of the control volume becomes delta X varies in the X direction and delta Y varies in the Y direction. And even the distance between the grid points, this delta XE, delta YN, in a non-uniform Cartesian grid, this delta XE varies in the X direction for a non-uniform Cartesian grid, and this delta YN varies in the Y direction in a non-uniform Cartesian grid. This details are presented in my previous lecture. So note that we don't want to use different running indices not only for flow properties but also for the geometrical parameters. So the width of this control volume UE is basically the width in the X direction is the distance between the circle, yellow circle capital E and capital P. And in the previous topic, the way we had been following, the distance between this yellow circle capital E and capital P, we call this as delta XE. So note that for the staggered U control volume, the width in the X direction is this delta XE. Note that there in the previous topic, we have used two delta. This bigger delta, which is shown here, is corresponding to the width of the control volume. This small delta is corresponding to the distance between the neighboring grid points. Okay, so this is a control volume which we have been using in the previous topic. So the width is this delta X P and delta Y P. But when you consider staggered control volume, note that for the U control volume, the height is remaining same as this yellow control volume. The height of this green control volume is same as the height of the yellow control volume. So this delta YP is the same width, but in the X direction, the width is this will matter only for a non-uniform grid. For uniform grid, it will not matter. So for non-uniform grid, it is presented here that this width, as per our earlier geometrical parameter that we have defined, that we want to extend to this staggered grid to provide the complexity in the programming. This width is not this delta XP. Now this has changed to this delta XP. Similarly, when you consider the V control volume, you can see that the width of the horizontal width of the V control volume is same as the horizontal width of the yellow control volume. So this horizontal width, this delta XP, this delta XP is same. But when you consider the vertical height of the V control volume and the yellow control volume, this height is different in this two control volume. Here it is delta YP, and here the height of this control volume is distance between these two yellow circles, P and N, that we have defined in our previous topic as delta YN. So we are using the same. So here I am presenting the formulation and the finite volume method on a non-uniform Cartesian grid. However, the final solution methodology that I'll be presenting in the next lecture, which is the part 2 of this lecture on CFD on a staggered grid, it is presented on a uniform grid. So this difference in the horizontal width for a non-uniform grid is highlighted here as this delta XE, and delta bar n. So here I am showing you, if you consider, let us suppose this is for a Cartesian geometry problem. This is a Cartesian, you have a problem where this is a Cartesian domain, where this is the left boundary, and this is the right boundary, this is the bottom boundary, and this is the top boundary, and inside this domain there is some fluid flow that is occurring. So if you draw a uniform Cartesian grid, you basically draw equispaced vertical lines, equispaced horizontal lines, and then you locate the centroids, which corresponds to the yellow circle, which are like the control volume for pressure. And here it is shown that the pixel for the u velocity corresponds to the vertical phase center. So all the squares that have been shown are like the pixels for u velocities. And the pixels or the grid points for v velocity is basically these triangles which are located on horizontal phase center. So all the triangles are shown as the grid points or pixels for v velocity. So for a complete domain, this figure shows the grid points for u velocities as square, v velocities as triangles, and circles as the grid points for pressure, and which is staggered. Grid point is not same. In the previous topic, which I had presented on finite volume method for CFD, note that I have considered yellow circle as the grid point for velocities as well as pressure. However, for the staggered grid, here you can see that the grid point of velocity is not same and it is present differently by squares and triangle as shown here for the complete. So with this, I had completed the I started with the challenges. That was the first section, 6.1. And then I had moved to the section 6.2, which was on a staggered grid, which was proposed as the first remedy for the pressure velocity decoupling. And in the section 6.3 of the part 1 of this lecture on CFD for a staggered grid, I'll finally present the physical law and discrete math-based finite volume method for a staggered grid. Note that in the previous topic also, which was corresponding to lecture 19, I have already presented this physical law and discrete math-based finite volume method, but that was presented for only one pixels or one grid point circle, not only for pressure but also for velocity. However, for a staggered grid, the finite volume method becomes a little different, so it is presented here for a staggered grid. So I'll follow the same sequence that I had used in lecture 19. I'll present this finite volume method first from mass conservation law, and then I'll apply it for momentum and energy conservation law because they have certain commonality as far as the advection and diffusion process is concerned. So basically I am extending what has been presented in the previous lecture number 19 to this lecture number 20. But here the difference is that the pixels for u velocity is this green squares and the triangles are the pixels for v velocity. The finite volume method gets slightly modified and the modifications will be highlighted in this lecture. So for mass conservation, for incompressible flow, you want to basically calculate net net mass flow rate leaving across the surface of the control volume. So this is the product of mass flux into surface area for a non-uniform grid. And for a non-uniform grid, when you use first approximation, you basically convert the normal velocities at the centroid of the surface area, u, uw, v, and vs. And then you need a second approximation to calculate u velocity here on the vertical phase center. You need second approximation to calculate v velocity here. But now in a staggered grid, you find that the pixel for u velocity is located at this u small e and u small w. The pixel for v small n and v small s is already located. So you substitute the values if you need some value at some point, and if you already have a pixel or a grid point, you don't need any approximations. Okay. So you note that this is an exact representation, there is no approximation. So ue is equals to u capital P. Note that this capital P is as per the convention that we are following. Okay, so this is UP, this is UW. So this U is UP, U small w is U capital W, V small n is V capital P, and V small n is V capital S. So note that by staggered grid, you have completely avoided the second approximation for mass conservation, for mass flux in the mass conservation equation. This is the final algebraic form of the mass conservation law. So this is the mass conservation equation that we have obtained, presented here for a non-uniform. Note that the pressure velocity decoupling I had presented earlier for a uniform grid, but whatever I have discussed philosophically, the same is also applicable if you consider a non-uniform grid. And however, if I had to present the pressure velocity decoupling, it comes out much less clearer. So that's why I have considered a uniform grid while presenting the idea of the pressure velocity decoupling. Because note that in a uniform grid only, the UP cancels down and you get velocities of alternate grid points as well as pressures at alternate grid point. So in a uniform grid, I can show very clearly the algebraic formulations and discuss the pressure velocity decoupling. However, that is also applicable for a non-uniform grid. However, it is less clear. So that's why I have presented the pressure velocity decoupling for a uniform Cartesian grid. And here I am presenting the finite volume method for a non-uniform Cartesian grid, which can be easily converted for a uniform grid by replacing this delta yp as delta y, delta xp as delta x. From the mass conservation law, let us move on to the transport process by the momentum and energy conservation law, where we will use advection and diffusion. But other than this, we'll also need to take care of pressure. Let us start term by term. First, we'll take the finite volume method for the unsteady term. There are two rates of change. The first rate of change leads us to the unsteady term. The second rate of change leads us to the advection term. The first rate of change of momentum or enthalpy is stored inside the control volume. So here, this is the control volume, green control volume, where we are applying the x momentum conservation. This red control volume, which is staggered. This x and y control volume are staggered with respect to the pressure or temperature control volume. So the height of this green control volume is same as the height of this control volume for energy or pressure, and the horizontal width of this V control volume is same as that of this control volume for pressure and energy. That's why this I would like to highlight, especially for non-uniform Cartesian grid. It doesn't matter for a uniform Cartesian grid. As presented in the previous slide, the previous lecture number 19, here for a staggered grid, the rate of change of momentum or enthalpy stored inside the control volume. I have presented here in a generic form, where this C is 1 and this phi is U, you get for x momentum, and if it is C is 1, phi is V, you get for y momentum, and if it is C is Cp and phi is T, then you get for energy equation. However, this volume is presented different for the three staggered control volume if you consider a non-uniform Cartesian grid, and this is the volume which is shown here, and the difference is highlighted here for the two control volumes. From the first unsteady term, if we move to the next unsteady term, which is corresponding to the advection term, it corresponds to the net momentum or enthalpy flow rate leaving across the surface of the control volume. So let us start one by one. Let us start with x momentum, then we'll go to the y momentum, and then we'll go to the energy. So we are from the unsteady term, we are going to the advection term. And for x momentum, this corresponds to net x momentum flow rate of the fluid leaving across the surface of the control volume. So we apply the x momentum conservation. If you have to calculate x momentum flow rate, you have to consider the green control volume. So here I am showing you the green control volume with horizontal width as this delta xc and vertical width as delta yt. So as I presented in the previous lecture 19, this is the type of arrows that we consider for the x momentum flow rate. Note that the final sense of the arrow is horizontal. So this is the x momentum flow rate entering from the left surface, leaving from the right surface, entering from the bottom surface, and leaving from the top surface. When you do a balance to calculate the net x momentum flow rate leaving across the surface of the control volume, so you get the total advection. This is the net X momentum flow rate living across the surface of the control volume, where you are multiplying that X momentum flux with the respective surface area. This is you are multiplying the for the vertical surface, and this is for the horizontal surface. And for this advection fluxes, as I presented in the previous topic, we use certain advection fluxes. Here I am presenting the advection term for the FOU, first order upwind scheme. So if the mass flux is in the positive x direction on the east surface, then the U small e is equals to U capital P, and if it is negative x direction, U small e is equals to U capital E. So this is UP and this is UP. So this has been shown from the first order upwind scheme for simplicity. And where you also need to know that you don't need mass flow rate only for the mass conservation, you also need for the momentum conservation, because momentum flow rate is given as the product of mass flow rate into u velocity. So for this control volume, when you want to calculate the mass flow rate for this control volume, you have to know the mass flux mx on the vertical surface and my on the horizontal surface. That's why in the mass conservation, I have used a different symbol only as mx. For x momentum conservation, this mass flux, I am using additional subscript mux, because it is like the grid point of mass flux for the three different control volumes, mass conservation, x momentum conservation, and y momentum conservation. The grid point for mx, my is different. Okay, so note that here to calculate the mass flux, like here to calculate mx, you will need u here. Now you don't have a green square here. So to calculate u at this point, which is ue for this control volume, this will be given as u capital E plus u capital P divided by 2. This I presented for a uniform grid. For a non-uniform grid, Cartesian grid, this is instead of dividing by 2, it will consist of non-uniform width of the control volume. So, so U small e here is to calculate the mass flux and the x direction on the east surface. U small e is equals to U capital E plus U capital P by 2. U small w will be U capital P plus U capital W divided by 2. And to calculate V here, the nearest V velocities is V capital E plus V capital P by 2, which is shown here. V capital E plus V capital P by 2. The V has to calculate mass flux here, MVy on the south surface is MVSC plus Vs divided by 2. So note that to calculate the mass fluxes for the x momentum conservation, we are indeed using linear interpolations. So we have avoided the linear interpolation for mass flux only in the mass conservation. For the momentum conservation, we have to do linear interpolation, and this does not create any problem of pressure velocity decoupling. So note that staggered grid avoids linear interpolation for mass flux only for mass conservation, not for momentum conservation. For momentum conservation, as shown here, we use linear interpolation to calculate mass fluxes. And here again, I'm highlighting the geometrical parameter which is different for non-uniform Cartesian. If you consider the advection term for the y momentum conservation, then you have to basically calculate the net y momentum flow rate of the fluid leaving across the surface of the control volume. And to calculate that, I have presented in the previous topic that the the y momentum flow rate is shown here when the final sense of arrow is in the vertical direction. This is the y momentum flow rate which is entering from the left surface and leaving from the right surface. This is entering from the bottom surface and this is leaving from the top surface. And if you do a balance, this will give the net y momentum flow rate leaving across the surface of the control volume. This y momentum flow rate we are calculating on a red control volume in which we are applying the y momentum conservation. And here again, if you use a first order upwind scheme to calculate V velocity on the east surface, if it is positive x direction, this will be Vp, and if it is negative x direction, it will be Ve, which is shown here, Vp and Ve for first order upwind scheme. So for first order upwind scheme, I am showing you how do you calculate the y momentum flux on the various surfaces of the control volume. And here again, to calculate the mass fluxes, I am using a different symbol with a subscript V. Note that the subscript for mass flux is for continuity equation or mass conservation, we are using only mx, my. For x momentum, the symbol used is mux, mv, mux and muy. For y momentum, the mass flux that is involved is presented here as mvx and mvy. For mx, my in the staggered grid, we don't have to do any interpolation. In the previous slide, I had shown you for mux and muy, you have to do linear interpolation. In this slide, I am showing you for mvx and mvy, then you have to calculate mvx on this grid point. To calculate mvx on east surface, which is this, when you want to calculate mvx, mass flux in the x direction for v control volume, you will need u velocity. In order to calculate u velocity, the nearest pixel for u velocities are this green square. So u small e here is equal to u capital N plus u capital P divided by 2 for a uniform grid. So for a uniform grid, I'm showing you here. By linear interpolation, you can calculate ue here. You calculate uw here by using this 2. Here, when you have to calculate v velocity, because in mass flux the normal velocity is involved, this will be v capital E plus v capital P v capital N plus v capital P divided by 2 here. And when you have to calculate v here, it is v capital P plus v capital S divided by 2. So this way, this slide shows you the linear interpolation that we use for mass fluxes in the y momentum equation. Here again, I'm highlighting for a non-uniform Cartesian grid, the width of the control volume that is involved. Now, from x momentum conservation, y momentum conservation, if you consider advection for energy conservation, then you get enthalpy flow rate. In the momentum conservation, it's momentum flow rate. For energy, it's an enthalpy flow rate. So this is the enthalpy flow rate in the vertical direction. This is the enthalpy flow rate in the horizontal direction. This AT is the enthalpy flux. So when you do a balance, you get net enthalpy flow rate leaving across the surface of the control volume. Here again, if you apply the first order upwind scheme, you end up with this equation. And the mass flux that are involved for the yellow control volume, you don't need any interpolation. So in the previous slide I had shown you the mass flux that is involved in the green control volume for x momentum conservation, red control volume for y momentum conservation. The mass flux were symbolically represented by mux for green control volume, mux, muy, and for red control volume it was mvx and mvy. For this yellow control volume it is mx and my. And for this control volume, note that for mass flux we do not need any interpolation because the pixels for the normal velocities are located wherever we need to calculate the mass fluxes. So finally, this slide shows you I initially showed you separately the x momentum flow rate balance, the y momentum flow rate balance, and the enthalpy flow rate balance. And here I am showing you together. So here, finally, you obtain net x momentum flow rate leaving across the surface of the control volume. This is for y momentum flow rate leaving across the surface of the control volume. This you had applied on a green control volume. This you had applied on a red control volume. And for enthalpy flow rate, you consider the yellow control volume, and you calculate the net enthalpy flow rate leaving across the surface of the control. After unsteady and advection, we are into the diffusion, which corresponds to the random motion of the molecule-based transport process, where along with conduction, we consider the viscous forces. And here the thermophysical property is K for conduction and dynamic viscosity mu for the viscous forces. So this is a green control volume where we'll apply the x momentum conservation to calculate the viscous forces acting in the positive x direction. Now in the green control volume, this is the yellow circle P and this is the yellow circle E, and the way we define the geometrical parameter for a non-uniform Cartesian distance, Cartesian coordinate, the distance between the yellow circle P and E, distance we denote it as delta xc. So the horizontal width of this green control volume is delta xc, and vertical width is same as that of the yellow control volume, that is delta y. Now this is used a general symbol small d with a subscript u for x momentum conservation. Du represent the viscous stresses in the x direction, And when you multiply the viscous stresses with the respective surface area, you get the net viscous forces. Where this du, as I mentioned, is represent the viscous stresses, you can see all the sigma. The second subscript is x. The first subscript correspond to the plane, where these are the normal stresses and these are the shear stresses. So all the viscous stresses have been expressed in terms of the normal gradient of u velocities, where note that when you take the u capital E minus u capital P, this is corresponding to the width of the yellow control volume, which is delta xe. So that's why this delta xe is in the denominator, not the, there are two delta. There is a, in earlier topics, we had a small delta here and you have a small e here. But in the staggered control volume for a non-uniform Cartesian grid, the distance between these two green square is corresponding to the horizontal width of the yellow control volume, which is delta x e. So that is coming here. So this is the gives you the discretized form of the viscous stresses in the x direction on the east face, west face, north face, and the south face, and this is the total viscous forces that you can calculate. This is the green control volume to calculate viscous forces acting in the x direction. When you want to calculate viscous forces acting in the y direction, for y momentum conservation, you have to consider the red control volume, and for the red control volume, the width, horizontal width is same, but the vertical height is different, which is corresponding to the yellow circle P and N. So this is delta yn. And these are the arrows that you have to consider to calculate the viscous forces in the y direction. So this dV now consists of sigma, where the second subscript is y, corresponding to the viscous stresses in the y direction. And these viscous stresses are expressed in terms of normal gradient of v velocity with a constant of proportionality of mu. So this shows you this is the discretized form on a finite volume method on a staggered grid. Finally, for the energy equation, the diffusion dt represents the conduction heat process. Note that there is a mistake here. This arrow should be in the negative direction, because this diffusion we are presenting here as minus of Q. I have discussed this in my previous lecture number 19, why we are considering D as minus Q, because it so turned out that in the previous topic on computational heat conduction, to calculate net conduction heat transfer rate, we have taken conduction influx, but when here we are generalizing as diffusion, we have to consider outflux. So that's why we represent the diffusion flux as minus of Q. So that's why the arrow here should be in the negative X and the negative Y direction. So finally, this is the viscous stresses in the X direction used in X momentum conservation. This corresponds to the viscous forces in the Y direction for Y momentum conservation, and this is corresponding to the total heat gained by conduction used in the energy equation. So this gives you the total diffusion term, finite volume method for the diffusion term on a staggered grid. After unsteady advection and diffusion term, finally we are into the source term, which corresponds to the pressure force for the momentum conservation and volumetric heat generation for the energy equation. Now, to calculate the pressure force in the x direction, we basically consider the green control volume with a green square as the pixel for u velocity up. And now you can see that when you want to calculate the pressure forces by considering the pressure at the surfaces, the pixel for the pressure is already defined in the staggered grid. So P small e is P capital P, and P small w is P capital P, P small is P capital E. So this gives you the net pressure forces acting in the x direction. Similarly, when you want to calculate in the y direction, you consider red control volume, and you can calculate net pressure force in the y direction by using this. So you can see that the second approximation for x momentum for pressure in the x momentum conservation and in the y momentum conservation, you don't need the linear interpolation because you already have the pressure grid points located at the vertical phase center for the green control volume and horizontal phase center for the red control volume. So you can calculate without using any second approximation, that is linear interpolation for pressure, you can calculate the net pressure force in the x and y direction for the momentum conservation. For the energy conservation, this gives you the net volumetric heat generation, which is presented here. So finally, I want to highlight that in the mass conservation and in the pressure term, you don't need any, you don't use no second approximation for normal velocity and pressure in a staggered grid. Although for we need mass fluxes, not only need mass fluxes in the mass conservation, we also need mass fluxes in the to calculate the x momentum flow rate and y momentum flow rate, for which I have used a different symbol, mu, mv, and for which we use a linear interpolation. So note that here for mass conservation, the velocities that you encounter are the adjacent grid point values. The velocities at adjacent. The pressure is adjacent. P and E, there is no yellow circle between P and P and N. So this P and, so the pressures are adjacent pressure. The normal velocities are adjacent grid points velocities. So this way we avoid the pressure velocity decoupling. We do not give any scope of the algebraic formulation based on alternate grid points, which leads to the superposition of unphysical oscillatory velocity and pressure field in this staggered grid. And as I mentioned, the mass fluxes for U and V, we do a linear interpolation. This is presented here for a uniform grid. And for energy equation, the mass fluxes is basically corresponding to the mass conservation. So the yellow control volume is a scalar control volume, not only used for pressure but also for temperature. And for the mass fluxes which are involved for this mx, and you don't need any interpolation. Okay, so the mass flux you can see here. I am showing you that for yellow control volume, the symbol is mx. For green control volume, it is mux. For red control volume, where we apply the y momentum conservation, it is mvy, mvx and mvy. After presenting separately for the unstudied term, advection term, diffusion term, and source term, let me present the finite volume method on for a staggered grid together for x momentum conservation. This is the net rate of change of x momentum flow rate stored inside the control volume. This is the net x momentum flow rate leaving across the surface of the control volume. This is the net viscous forces acting in the positive x direction. This is the net pressure force acting in the positive x direction. For y momentum conservation, the algebraic equation that you derive from the y momentum conservation law, this is the net y momentum flow rate stored inside the control volume. This is the net y momentum flow rate leaving across the surface of the control volume. This is the net viscous forces acting in the y direction. This is the net pressure force acting in the y direction. From x momentum conservation, y momentum conservation, when you apply the energy conservation law and using the discrete math, when you do an algebraic formulation, the final algebraic equation that you obtained is presented here as an energy equation. So the energy equation, the first term is this represents the rate change, then the rate of change of the enthalpy stored inside the control volume. The second rate of change is the net enthalpy flow rate leaving across the surface of the control volume. This is equals to the total heat gained by conduction plus the total heat gained by volumetric heat generation. So after presenting, first I showed you unstudied terms separately, advection, diffusion, and then source. Then I showed you x momentum conservation, unstudied, advection, diffusion, source together. And finally, I am showing you here all the possible combinations: unstudied term, advection term, diffusion term, source term, for x momentum conservation, y momentum conservation, and energy conservation. So on a staggered grid, note that we apply the x momentum conservation, which is shown here for the green control volume. We apply the y momentum conservation to this red control volume. We apply the energy conservation to this yellow control volume. So this is for x momentum conservation, this is for y momentum conservation, this is for energy conservation. This yellow control volume we also use for mass conservation. The mass fluxes, you don't need any interpolations for this normal velocities for mass flux in this yellow control volume. But note that we need the linear interpolation for the mass fluxes in this red control volume and green control volume. This is the final algebraic equation that you can derive. So this is the physical law and discrete math based finite volume method for a staggered grid. This is presented in a generic form: unstudied term, advection term, total advection, total diffusion, total source, where if this phi is u, you can basically the x momentum equation. When I say x momentum equation, I mean the algebraic equation. This is the y momentum equation. This is the energy equation in an algebraic form, where this advection is, this phi AU is for x momentum advection and x momentum AU is for y momentum and AT is for energy. This is presented here, and the pressure force are involved in the momentum equations. These are the source term. So with this, I had come to the end of this lecture. The details can be found in chapter 9 of this book, Introduction to Computational Fluid Dynamics, Development, Application Analysis. You can download the supplementary material from this website, and much more detail is presented in this book. In this YouTube channel on CFD Made Easy, I have presented some of the key ideas corresponding to this book. But if you want to really develop your own computer program, there are a lot of nuts and bolts which I call as implementation details, for which you can refer this book to get a better idea to develop your computational skill and to create your own CFD software, so that you can you can be a creator rather than be a part of creation. Thank you for your attention.